In the last few lectures, we dealt with the atomic nucleus. We learnt that the nucleus consists of neutrons and protons. The chemical properties of the nucleus are determined by the number of protons in the nucleus, and this number is called the atomic number of the nucleus. We pointed out that in a nuclear reaction, the mass number A and the atomic number Z are conserved. Nuclei in the range from 55 to 60 are the most stable ones. Lighter nuclei combine together, that is, they undergo fusion, so that the product nuclei are more stable. On the other hand, heavier nuclei undergo fission, so that the products are more stable. We studied radioactivity and in particular the interesting subject of carbon dating. Today, we start with the study of semiconductors. We shall first of all distinguish between conductors, insulators and semiconductors. So, to start with, let us see what free electrons are in the metals. We know that metals have generally high densities. That means that the atoms are very tightly packed. The outer shells of electrons get crushed against one another. Imagine you see a lot of outer shells, a huge number, and they are pressed against one another. Then the outer shells get crushed against one another. The consequence is that the electrons which were in these outer shells, they become delocalized. That means, they do not belong to any particular atom. These electrons are called free electrons, because they do not belong to any particular atom. They can move in between the nuclei. You see here these small dots are electrons. They can move in between the nuclei and they are called therefore free electrons. Because of a large number of free electrons, metals are generally very good conductors of electricity. At the other end are substances which are called insulators. Their conductivity is very poor, and in between these are substances like silicon and germanium, which have conductivity in between these two. These are called semiconductors. So, broadly speaking, here is the distinction between metals, semiconductors and insulators. Metals have conductivity between 10 to the power 2 to 10 to the power 8 Siemens per meter. Semiconductors have conductivity between 10 to the power 5 to 10 to the power minus 6 Siemens per meter, and insulators have conductivity between 10 to the power minus 11 to 10 to the power minus 19. See that the ratio, huge ratio. That means, metals are very good conductors, insulators are very poor conductors, and semiconductors are in between. At the kind of high densities that we have in metals of these free electrons, the electrons become degenerate. Therefore, their average energy is typically of the order of electron volts, much larger than the typical thermal energies. We calculate here the thermal energy at 300 K, for example, and you can calculate K B times T, where K B is Boltzmann constant and T is temperature. This thermal energy is of the order of 10 to the power minus 2 eV, compared with the energy of the degenerate electrons, which is of the order of a few MeV. Now, imagine this degenerate electron gas. Let us concentrate on one electron, this black one. This is surrounded by the red ones, and they all have electric field. They all attract this electron, they all exert Coulomb field on this electron, and all this Coulomb field cancels, because there are large number of electrons, and therefore, this particular electron and any other electron for that matter does not feel the electric field of the other electrons. Therefore, they do not interact, and one can say that the electron gas behaves like a perfect gas, because the electrons do not interact. An electron must obey Heisenberg's principle of uncertainty. This we have done earlier when we were doing atomic physics. The principle implies that if an electron has position between x and x plus dx, then at that instant it must have momentum between p and p plus dp. The uncertainties in the position and momentum, that is delta x and delta p respectively, their product is of the order of h by 2 pi, where h is Planck's constant. H by 2 pi is also sometimes written as h cross. We may say that each electron is confined to a region of space which we might call a cell of magnitude h in the x p plane. I will show you in a moment. The x p plane is called the one dimensional phase space. In 3 dimensional phase space, the cell would have a volume h cubed here. You see, this is p axis, this is x axis, this is phase space in 1 dimensions, and this is the uncertainty in momentum, this is the uncertainty in position, and therefore, if we have a cell h, this h will have 1 or 2 electrons. 1, 2, because Pauli's exclusion principle says that no 2 electrons can be in the same state. So, in this cell we shall have 2 electrons, one with the spin momentum in one direction and the other with the spin momentum in the opposite direction. Why? Because Pauli's exclusion principle says that no 2 electrons can have the same quantum state. They must differ by at least one quantum number, and here they differ by the direction of s. In one the s may be like this, in the other the s may be in the opposite direction. All particles with spin half, 3 by 2, 5 by 2, etc. in units of h cross are Fermi particles. These particles are called Fermi particles. They have spins half, 3 half in units of h cross. So, electrons, protons and neutrons and their antiparticles, that is anti-electron, anti-proton, they are all Fermi particles. Even atoms and molecules consisting of an odd number of Fermi particles are called Fermi particles. For example, He3, helium 3 is a Fermi particle because it contains 3 Fermi particles. According to the exclusion principle, no 2 electrons can have all quantum numbers the same. That is, the 2 must have at least one quantum number which is different. It implies, as I have been saying, that no 2 electrons can occupy identical quantum states. So, here are those cells again. This is delta p, this is delta x, this is a p axis, this is the x axis, and each cell in 3 dimension has a volume h cubed, but can contain only a maximum of 2 electrons, one having spin pointing upwards and the other pointing spin downwards. So, we have 2 here, maximum of 2. Some of these cells may have only 1 electron. How many electrons are there in this phase space? You see, we can find the volume of this and multiply that by 2 between p and p plus dp, find the volume and multiply that by 2 and we get, and of course, divide by h cubed, the volume of each cell, and that gives us the number here. NP-dp, the number density of particles between momentum p and p plus dp, is the volume between p and p plus dp, that is 4 pi p squared dp, divided by h cubed to find the number of cells, and each cell contains 2 electrons. Therefore, NP-dp is 2 by h cubed into 4 pi p squared dp. You see, this is the sphere with radius p, and the outer sphere has radius p plus dp, and the volume between these two is 4 pi p squared dp. 4 pi p squared is the surface area multiplied by dp gives us the volume, and in this volume the number density of particles is NP-dp. On the other hand, at low densities, the number of particles of momentum between p and p plus dp is given by the classical Maxwell-Boltzmann distribution. If n is the overall density of electrons, this number at temperature T is given by NP-dp. This is for Maxwell-Boltzmann distribution, and this number is 4 pi n, where n is overall density, divided by 2 pi m k T. M is the mass of the electron, k is the familiar Boltzmann constant, and T is the temperature. So, at this temperature at T, the number of particles having momentum between P n p plus d p is this number. And now, it is a competition between this number and this number. As long as this number is smaller than this number, there is no problem. However, if this number, the number density of particles between P and P plus d p given by the Pauli's exclusion principle, if this number is much larger than this number, then Maxwell-Boltzmann distribution is no longer valid. The Maxwell-Boltzmann distribution breaks down and there is a new distribution that comes into play. When this Maxwell-Boltzmann distribution breaks down, we say that the gas has become degenerate, and the property of the degenerate gas is that the particles rush to occupy the lower energy states. Here again I show you that number again, this cells and x and p, and you see what I have been saying, that the property of a degenerate gas is that the particles rush to occupy the low lying energy states. Up to this red line, all energy states are full, you can see that, and above this there are only a few states which are full. This is called a degenerate gas, and this state, momentum of this state up to which all the states are full, all the cells are occupied, is called the Fermi momentum, and energy corresponding to the Fermi momentum is called Fermi energy. So, up to Fermi energy, all states are completely full. Over this, only a few states are occupied. Here, this was the original Maxwell-Boltzmann distribution. I think you are familiar with the Maxwell-Boltzmann distribution, and as more and more electrons are pushed into a given volume, that is, the number density is increased, then this gets modified first to this, and when this number n p d p given by the exclusion principle is much greater than the number given by the Boltzmann distribution, then this distribution breaks down completely and we have a new distribution like this. What is this distribution? You see, below P f all these states are full, and beyond P f only a few states are occupied. In this table, I am giving the free electron density, Fermi energy and Fermi velocity of the electrons for metals like copper, iron, aluminum, gold and silver. The point to note is that Fermi energy is of the order of a few, in fact several eV. In the case of iron it is 11, in the case of copper it is 7 eV and like that. So, the Fermi energy is of the order of, in this case, say 10 eV. To explain the concept of this degeneracy, let us look at this example. Suppose you are in a hall and there are only few people, then you can occupy any seat that you like, as here you can occupy any seat. Now, suppose more and more people keep pouring inside the hall, then what happens? At a certain density of people inside the hall, there is a rush towards the low lying states, that is, all these front states are full and there are very few people sitting at these seats. So, this is the picture of a physical picture of a degenerate gas, that all the low lying energy states are completely occupied and there are very few particles occupying states beyond Fermi energy. The distribution that electrons obey when they are degenerate is called Fermi-Dirac distribution. This one, when the Maxwell-Boltzmann distribution breaks down and the energy becomes, the density becomes very high, then this distribution comes into play. This is Fermi-Dirac distribution, and this is given by F e equal to 1 by e to the power e minus E f by k t plus 1, where E is the energy of the particle, E f is the Fermi energy, K is Boltzmann constant, T is the absolute temperature, of course plus 1, where this Fe is called the occupation number. This is the probability of a particle having energy E. This is called the occupation number, and it can be easily verified that, note this plus sign, this Fe is either less than or equal to 1. At the most it can be equal to 1. Then if you differentiate this function, you find d of Fe by dE, you find this is less than 0. This means that the occupation number decreases as E increases. That is the property of a degenerate gas, that as to go to higher energy states, the occupation probability decreases. And in the limit t equal to 0, this is very interesting. In the limit t equal to 0, this is a step function. I will show you the function first. We have this step function. This is Fe, this is E, and this is the Fermi energy. And you see the step function is like this, that all these states are occupied at t equal to 0 and no state beyond that. How does this happen? Imagine t equal to 0. If E is less than Ef, then this factor, this term goes to 0 and Fe becomes 1. On the other hand, if E is greater than Ef, then this becomes infinite, this is negligible, and this becomes 1 by infinity, which is 0. So, Fe becomes 0. So, at t equal to 0, E is slightly larger than Ef, Fe is 0, you can see that, and E is slightly less than Ef, Fe is equal to 1. This is the Fermi-Dirac distribution at t equal to 0. That means all energy states are full up to Ef, and beyond that at t equal to 0, no state is occupied. If we relax this condition, say we make temperature slightly non-zero, then what happens? Then a few states beyond Ef also become occupied. You see, this distribution will help us in understanding how only a small increase in temperature can improve the conductivity of a semiconductor. You see, you can see the thing here, slightly non-zero temperature, and there are states above Ef which are occupied, and these electrons can move. So, therefore, there is a conductivity increase. In the next lecture, we shall continue with this, and we shall see how energy bands are formed in atoms. We shall take the example of sodium atom, and we shall also distinguish between valence bands and conduction bands, and we shall also see what intrinsic semiconductors are.